All right, in this video, I'm going to overview the procedure sections of Lab 2. So let's start with Section A, Earth's rotation. Now in this section, you're just learning how to set up the apparatus and figuring out what side of it you're on. Are you on the sunrise side or the sunset side? And that will be important for measurements later in the lab. To set up the apparatus, begin by taking the globe and moving it to within a few inches of the ring light. Once it's really close to the ring light, adjust the height of the ring light up and down until it precisely matches the height of the globe. Then you can back the globe out a few feet. Also move the globe in and out such that it's precisely lined up with the ring light. Once you've done this, if you have a dark colored towel, you may want to put it down between the ring light and the globe to minimize reflection off of the surface back up to the globe. And you'll want to turn the lights off in the room. If you have any windows, you'll want to block them up so no sunlight comes in. You really do need a dark space to make the measurements for this lab. Once you do all this, you should be able to see the terminator, the division between day and night. You can see it diagrammed here, but in reality, it can be a little bit more difficult to see. The transition is not abrupt, it's gradual, and you're going to have to use your best guess as to where it's at. Now, a couple things that can help. First of all, you can step back a few feet. If you step back a few feet, it sometimes makes it a lot easier to see. If you're still having difficulty placing it, look at the stand at the bottom of the globe. It should be directly lined up with the terminator, and you can use that as a reference point. Now, the last thing you need to do is to figure out if you're on the sunrise side or the sunset side of the apparatus. It depends on how you set it up. So the instructions here ask you to consider New York City and Los Angeles. We know that the sun rises first in New York City, then a few hours later, it rises in Los Angeles, and the sun sets first in New York City, and then that occurs in Los Angeles. So find New York City and Los Angeles, and make New York City emerge from nighttime first, followed by LA, and then half a day later, make New York City move into darkness, followed by LA, and then you should be able to determine what side of the apparatus you're on. If those two cities are emerging from nighttime into daytime on your side of the apparatus, you're on the sunrise side. If they're moving into darkness from daytime on your side of the apparatus, you're on the sunset side. Then you're asked two questions. As viewed from the top down, is Earth rotating clockwise or counterclockwise? And as viewed from the bottom up, is Earth rotating clockwise or counterclockwise? Okay, so now we're going to learn how to measure the first of the two primary effects that determines why it's hotter in summer and colder in winter, and this is length of day. So we'll begin with an example, and that example will be Chapel Hill, North Carolina, home of Skynet headquarters, and we'll measure the length of day in Chapel Hill on the summer solstice. So the first thing we need to do is reposition the globe into the northern hemisphere summer solstice configuration. In other words, you'll need to orient the globe, rotate the globe, such that the northern hemisphere is tilted towards the ring light, but still make sure it's precisely centered on the ring light. Once you do that, you'll want to move Chapel Hill to the terminator that's nearest you. It's either the sunrise terminator or the sunset terminator. So you can see an example here where I've taken Chapel Hill, North Carolina, put it on the division between day and night. Then the next thing you do is you go to the top of the globe and orient the hour circle such that noon points to the sun, points to the ring light. And then you're going to follow the line of constant longitude changing latitude from Chapel Hill all the way up to the ring light. And that will give you the time that it's on the terminator. You indicate whether you're on the sunrise or sunset side of the apparatus here, and you enter the time that Chapel Hill is on that terminator here. Enter the time in decimal hours to the nearest half an hour in the first box, and in the second box, you enter AM or PM. Now, if the time doesn't seem quite right, remember that this is what the time would be if there was no daylight saving time and if there were no time zones. So it should be pretty close to your intuition, but not exactly. Now, next, you're going to calculate the half length of day. So if you're on the sunrise side of the apparatus, you take whatever AM time that you measured and subtract that from the number 12. And that's the half length of day. In other words, if the sun rose at 6 a.m., the half length of day is 6 hours. If you're on the sunset side of the apparatus, you simply enter whatever PM time you measured here. And again, that's half the length of day. In other words, if the sun set at 6 p.m., half the length of day is 6 hours. Whatever you enter in this box, you double it. That gives you the length of day. And then we tell you the true length of day for Chapel Hill on the summer solstice. Here, it's 14.6 hours. So calculate a percent error and then discuss significant sources of error here. Once you've learned how to do this for one location and one season, you're going to pick 5 different locations. One near, but at least a little bit south, a few degrees south of the Arctic Circle. One in the middle of the Northern Hemisphere. You can reuse Chapel Hill. One near the equator. One in the middle of the Southern Hemisphere. And one near, but just a few degrees above, a little bit above the Antarctic Circle. Once you've selected your locations, you'll record them here in data table 1. And it's very important that you enter them from north to south. If you don't do this, the auto grading will get screwed up and you'll lose a lot of points. Then for each of your locations, you're going to want to estimate the latitude off of the globe, as you learned how to do in the background sections, and enter that information here. And then for each of your locations, you're going to measure the length of day, and you're going to do it for the Northern Hemisphere summer solstice, the Northern Hemisphere winter solstice, the Northern Hemisphere vernal equinox, and the Northern Hemisphere autumnal equinox. So for each season, you're going to have to reorient the globe with respect to the ring light. But once you've done that, for each location, you measure the length of day just as you practiced with the Chapel Hill example. You're going to first indicate whether you're on the sunrise or sunset side of the apparatus. You're going to enter the sunrise or sunset time here, calculate the half length of day, and then double it to get the length of day. Remember to report your sunrise and sunset times in decimal hours. And also, you may be able to guess the answers for the vernal and autumnal equinoxes. But that's not sufficient. You have to make the measurements yourself and then use them to verify what your guess may be. Once you've collected these measurements, we have an honor code pledge here. Sign your name to attest to the fact that you collected these data yourself. And then you'll go to our graphing website. There's a tutorial here to show you how to graph your data using this graphing application. Once you've plotted your data, you'll download it as a PNG file and then upload it to WebAssign here. Then in this box, you'll describe the data that you've just plotted. You'll discuss how length of day varies as a function of latitude for each of the 4 seasons that you've measured. Okay. Let's move on to part C. In part B, we measured length of day, which clearly has a big impact on how warm it gets. In part C, we'll measure how high the sun gets in the sky come midday, because that impacts the directness of the illumination, which also affects how warm it gets. For example, let's say this is the sun, and the wall back here is the ground. So if the sun is high in the sky, it's shining its light very directly onto the ground, and that light is concentrated. You have a high amount of energy per unit area if you're within that circle. If the sun is low in the sky, its light gets spread over a much larger area. So it's the same amount of energy, but spread out over a larger area. So you have a lower energy per unit area if you're in that region, and hence slower heating. So again, we're going to start with a practice example. Again, we'll consider Chapel Hill during summer solstice, first day of summer, and we'll learn how to measure how high the sun gets in the sky at midday. So first, put the globe back into its summer solstice, northern hemisphere summer solstice configuration, with the northern hemisphere pointed toward the ring light. Then rotate the globe such that Chapel Hill is pointed towards the ring light, the sun, so it's midday. Then take the protractor and place it flush on the globe against Chapel Hill. So this represents the local horizon. Down here is your southern horizon. Up here is your northern horizon for someone who's standing on the globe at this location. Now you'll have a string tied through the hole at the 0, 0 spot on the protractor. You want to hold that string horizontal, even with the table. Even if it doesn't point to the center of the ring light. That's because the ring light is so close. If you imagine the ring light much, much farther away, to point towards it, you would need to hold that string flush, so level with the table. And then you're going to measure the angle from the southern horizon up to the string. Now on the protractor, there are usually 2 scales, one running from 0 to 180 and one running in the opposite direction. You'll want to use the scale that starts with 0 on the southern horizon, then measure the angle up to the string. And that is how high the sun is in the sky at midday. You'll record that angle here. And the true value for Chapel Hill on the first day of summer is 78 degrees. The sun gets to 78 degrees above the horizon at midday. So calculate your percent error and put that here. And then discuss sources of error in this box. Once you've done that, we're again going to pick a number of locations on the globe, this time all in the northern hemisphere. One of these locations will be the North Pole, and then you pick 3 more locations. One location near the Arctic Circle, it can be a little bit above or below, a location between the Arctic Circle and the Tropic of Cancer, for example, Chapel Hill fits this category, and finally one near the Tropic of Cancer. And you can reuse cities that you chose from the previous section in the lab. Again, record your locations here in data table 2 and measure the latitudes for these locations off of the globe. And then again, you're going to measure, in this case, how high the sun gets in the sky at midday for each location and for each of the 4 seasons. Remember to reorient the globe before you do each season into the proper configuration for that season. And then for each location, measure how high the sun gets in the sky and enter that in these boxes. The only location you don't need to do is the North Pole during the Northern Hemisphere winter solstice, because the sun never gets above the horizon. The highest the sun gets is 23 degrees below the ground, and so you'll want to use -23 for this box. Again, there's an honor code pledge, so enter your name. Then you go to the graphing website, and you'll again graph your data. You make a plot of how high the sun gets in the sky, measured at midday, versus latitude, with one curve for each of the 4 seasons. You want to save it as a PNG file on your computer, and then upload it to WebAssign here. And then in this text box, describe your plot, describe your measurements, discuss how the height of the sun in the sky at midday varies with latitude for the 4 seasons. And then there's one more question. How would these results differ if you had chosen Southern Hemisphere locations instead of Northern Hemisphere locations? Okay. On to the final part of the lab. So in this section, we'll use what we just learned to measure the circumference and hence the diameter, the size of our planet. And this will then serve as the basis of the cosmic distance ladder in the labs ahead. So to do this, imagine going on a road trip between 2 locations on a relatively straight shot of road, and on a road that's oriented for the most part north-south. So you can go on this road trip and you can measure that length of road using your car's trip odometer. Now, you haven't driven completely around the globe, you've traveled just a fraction thereof, but using a little bit of geometry, we can extrapolate and figure out the circumference of the globe. Now, this is a geometry we're going to see time and time again in the labs ahead. And that is, if you cover a certain distance on the circle, that corresponds to covering a certain angle around the circle. And that angle, as a fraction of 360 degrees, is going to be the same as the distance covered as a fraction of the circle's circumference. And that's what we've written down here. We have the angular separation divided by 360 degrees, and that's equal to, in this case, the distance covered on the road trip divided by the circumference of Earth. Here we've solved it for circumference, and it depends on the distance traveled and the angular separation between those 2 locations. So let's consider a specific example. A road trip from Winnipeg, Manitoba, Canada, to Omaha, Nebraska in the United States. The first thing we need is the distance between those 2 locations, and you would get that by driving it in your car and then reading it off the car's trip odometer. Of course, I don't expect you to go and take this trip. Instead, go to Google Maps and look up the distance as you would drive it between these 2 locations, and be sure to read that off in kilometers, not miles, and enter that in this box here. Then the only other thing we need to calculate the circumference of the Earth is the angular separation between these 2 cities. And all that angular separation is the difference in their latitudes. Now you can measure this by measuring how high the sun gets in the sky at midday at each of these locations. It gets this high at the more northern location, and it gets higher up in the sky at the more southern location. If you measure these 2 angles, the height of the sun in the sky at midday, and subtract them, that's the same as the difference in their latitudes. So given the skills you learned in the previous section, I want you to measure how high the sun gets in the sky at midday in Winnipeg, put that here, and then the same for Omaha here. And you can do it for any season. The season doesn't matter, just use the same season for both cities. Subtract them, put that here. Then using the distance here and the angular separation that you just measured, calculate the circumference of Earth using this equation here. That goes here. Show your work in this box. Then take the circumference and divide it by pi, and that will give you the diameter of the planet, which you can enter here. And the true diameter of Earth is 12,742 kilometers. So using that, you can calculate your percent error. And then in this box, discuss significant sources of error. Finally, I want you to summarize what you've done and expand on it a little bit. I want you to discuss how you would measure Earth's diameter using nothing but a shadow casting stick, a protractor, and a car's trip odometer. If, again, you're on a road trip on a relatively straight shot of road that runs north-south between two locations. In particular, I want you to describe how you would know it's midday, not using a clock, but just using the shadow casting stick and the protractor. Okay, that's it for this video.